Good morning everyone. This is Deepanshi from BSc Chemistry on a second year. Today I am going to present a physical chemistry presentation. The topic of presentation is hydrolysis of salt.
Hydrolysis of salts. Water is dissociated to a very small extent into H positive and OH negative ions. In pure water, the concentration of H positive ions and OH negative ions are equal to each other. That is, the concentration of H positive is equal to the concentration of OH negative. Pure water, therefore, is neutral. Salts are strong electrolytes. When dissolved in water, they dissociate almost completely into positively charged ions, that is cations, and negatively charged ions, that is anions. In some of the salts, the anions of the salt react with H positive ions furnished by water, thereby lowering the concentration of H positive ions in solution. Since the product of H positive and OH negative ions is constant, therefore the concentration of OH negative ions in the solution increases. The solution therefore becomes alkaline. In the case of some other salts, the cations of the salt react with OH negative ions furnished by water, thereby lowering the concentration of OH negative ions in solution. Since Kw is constant, the concentration of H positive ions in the solution increases. The solution therefore becomes acidic. The phenomena of the interaction of anions and the cations of the salt with the H positive and OH negative ions furnished by water yielding acidic or alkaline or sometimes even neutral solutions is known as salt hydrolysis. Hydrolysis may also be considered as the reverse of neutralization. Neutralization, as we know, involves combination of OH positive and OH negative ions yielding undissociative water, that is, it involves almost complete disappearance of H positive and OH negative ions. Hydrolysis, on the other hand, leads to the formation of H positive or OH negative ions as discussed above. For a study of hydrolysis, it is convenient to divide the salt into four categories. That is, first, salt of strong acid and strong base, such as potassium chloride and sodium nitrate. Second, salt of weak acids and weak strong bases, such as potassium cyanide and sodium acetate. Third, salt of strong acids and weak bases, such as ammonium chloride and aniline hydrochloride. And last, salts of weak acid and weak bases such as ammonium acetate. Discussing about the first, salt of strong acids and strong bases, salts of strong acids and strong bases do not hydrolyze. Consider, for example, potassium chloride. When it is dissolved in water, its ion K positive and Cl negative have no tendency to react with the H positive and OH negative ions of water. This is because of the possible products of the some interactions, namely KOH and HCl are themselves almost completely dissociated. Consequently, there is no change in the concentration of H positive and OH negative ions, and the solution continues to remain neutral. Thus, salt of strong acids and strong bases do not undergo hydrolysis. Discussing about the second, that is salt of weak acid and strong bases, salts of this category undergo hydrolysis to give alkaline solutions. Consider sodium acetate as an example of this category. When dissolved in water, it undergo almost completely dissociation into Na and CH3COO negative ions. The acetate ions will take up some of the H positive ions furnished by the slightly dissociated water to form feebly dissociated acetic acid. CH3COO negative plus H positive will give acetic acid CH3COOH. The undissociated water further dissociates as to maintain the constant value of Kw is equal to concentration of H positive into concentration of OH negative. The H positive ions are again taken up by CH3COO negative acetate ions. This leads to the increase in the concentration of hydroxyl ions and decrease in the concentration of hydrogen ions. The solution therefore becomes alkaline. Thus, the aqueous solution of the salt of a weak acid and a strong base is alkaline because of hydrolysis. Hydrolysis constant The hydrolytic reaction of sodium acetate may be written as CH3COO negative plus Na positive plus H2O will give CH3COOH plus Na and OH negative. Since Na positive ion is common on both sides of the equation, it may be left out and the equation may be represented as such: CH3COO negative plus H2O plus OH negative free base and free acid CH3COOH. Applying the law of chemical equilibrium and taking the concentration of water as constant since it is present in large amount, we have Kh is equal to concentration of OH negative acetic acid divided by concentration of acetate ions. Kh is known as hydrolysis constant. Relation between Kh, Ke and Kw. It should be noted that ultimately when the equilibrium of the hydrolysis ion of CH3COONA is established, the following two equilibria having also to be satisfied. CH3COOH gives CH3COO negative plus H positive and H2O dissociates into H positive and OH negative. Therefore, the following equation should also hold good for Ka H positive CH3COO negative concentration divided by CH3COOH concentration, where Ka is a dissociation constant of the acid. Kw is H positive and OH negative dividing equations, and thus we get the relation between Kw and Ke. Evidently, the hydrolysis constant Kh of the salt varies inversely as the dissociation constant Ka of the weak acid. Therefore, the weaker the acid, the greater is the hydrolysis constant of the salt. Degree of hydrolysis. Discussing about the degree of hydrolysis, taking a C moles per liter be the initial concentration of sodium acetate in aqueous solution, and let X be the degree of hydrolysis, which is defined as the fraction of the total salt that has undergone hydrolysis on the attainment of equilibrium. Rewriting the hydrolysis equation as before and putting the equilibrium concentration of the various species, we have this: CH3COO negative plus H2O will give CH3COOH plus OH negative. If X is a small as compared to unity, 1 minus X is the above equation may be replaced by 1, so that we get Kh is equal to Cx square, and ultimately X is equal to Kw by Ka into C under the root. By means of equation 6, it is possible to calculate the degree of hydrolysis of a salt, of a weak acid and a strong base at any concentration C of the salt, provided the dissociation constant Ka of the acid is known. It is also follows from equation 36 of the water of weaker the acid, that is smaller the value of Ka, the greater is X, the greater is hydrolysis. Also, since Kw increases rapidly with temperature and Ka changes only slightly, it is evident that the degree of hydrolysis increases considerably with the rise of the temperature. Lastly, it is seen that the degree of hydrolysis increases when concentration decreases, that is, when dilution increases. Taking the third part, this is salts of weak bases and strong acids. Consider ammonium chloride as an example of this category of salts. In water, the undergoes almost complete dissociation into NH4 positive and Cl negative ions. The ammonium ions take up OH negative ions furnished by water to form the feebly dissociated base, ammonium hydroxide NH4OH. The undissociated water further dissociates so as to maintain the constant value of Kw. This causes an increase in the concentration of hydrogen ions and a decrease in the concentration of hydroxyl ions. The solution therefore becomes acidic. Thus, an aqueous solution of a salt of a weaker base and a strong acid is acidic because of hydrolysis. Hydrolysis constant. The hydrolytic reaction of ammonium chloride may be represented as NH4 positive plus Cl negative plus H2O will give NH4OH plus Cl negative and H positive ions. Applying the law of chemical equilibrium, we have Kh is equal to H positive NH4OH divided by NH4. Dividing equations 40 by equation 39, we get Kw by Kb is equal to H positive NH4OH divided by NH4 positive is equal to KH. KH is equal to Kw by Kb, and this is evident that the weaker the base, the greater is the hydrolysis constant of the salt. Degree of hydrolysis: if C is the initial concentration of the salt in moles per liter and X is the degree of hydrolysis on the attainment of equilibrium, then the concentration of the various species at equilibrium will be represented as NH4 positive plus H2O will give NH4OH plus H positive. If, as before, x is too small as compared to unity, kh is equal to cx square, and we get the value of x is equal to kh by c under the root. As in the previous case, the degree of hydrolysis of a salt at a given temperature is more if the base of weaker, that is, if Kb is smaller. Also, x increases when concentration decreases, that is, dilution increases. Further, since Kw increases much more with temperature than Kb, the degree of hydrolysis at a given concentration increases with rise in temperature. The fourth part, we have the salt of weak acid and weak bases. Salt of this category may be exemplified by ammonium acetate. The NH4 positive and CH4O negative CH3COO negative ions furnished by the salt combine with OH negative and H positive ions of water respectively to form feebly dissociated NH4OH and CH3COOH. The reaction may be represented as CH3COO negative plus NH4 positive plus H2O will give CH3COOH plus NH4OH. In this case, both H positive and OH negative ions are removed simultaneously, and if they are not removed in equivalent amount as in the present case, the solution remains neutral, although hydrolysis of the salt is taken place. The equilibrium law equation of hydrolysis constant in the present case may be written as Kh is equal to CH3COOH NH4OH divided by CH3CO negative NH4. The following other equilibria also exist in solution as following. CH3COOH will give CH3CO negative plus H positive. NH4OH will give NH4 positive plus OH negative, and H2O will give H positive and OH negative. Accordingly, the following equation should be as follows. Ka is equal to this CH3CO negative H positive CH3COH. Following the ways Kb and Kw are also can be calculated. If the initial concentration of the salt is C moles per liter and X is the degree of hydrolysis, then the equilibrium point, the concentration of the various species will be calculated as shown below.